we switch gears away from file systems and go towards facility strategies, right? So it's about the APS, Nicholas. Yes.
Okay, great. Excellent, thank you. So yes, my name is Nicholas Schwarz. I'm the group leader for scientific software engineering and data management at the Advanced Photon Source. And I'll spend a little bit of time today talking about developments we've made realizing our scientific computing strategy, especially in light of the newly upgraded facility. So for some context, the APS has just replaced its storage ring with a new MBA-based lattice design. This will provide a higher brightness, increased coherence, and higher energy storage ring and synchrotron light source. Oh, sorry. In addition to this, we've also have underwent upgrades of many of the instruments at the facility. So we have 9 new feature beamlines that are currently being built in commission, and there are 15 large-scale enhancement projects that are underway. And so what all of this has done for us in terms of computing is it's really increased the potential to create a lot more data. Prior to the upgrade, we collected somewhere in the single digits of petabytes of raw data per year. And now, especially because of detectors and the increased brightness, we have the potential to collect hundreds of petabytes of raw data per year. And that, of course, necessitates a lot of advances in computing to really take advantage of that and the full potential of that. And so we've organized our efforts in computing really around a big goal, which is to harness the power of computing and the value contained in data to elevate the overall impact of the facility and the operational efficiencies of the facility. And that's brought us to identify 5 strategic goals in the computing space that we want to achieve. To enable high-speed discovery, to reduce the time it takes to deliver science, to unlock exceptionally challenging experiments, to leverage this explosion of data for potentially new science that goes beyond what one individual experiment or measurement can do, to fully empower our users with cutting-edge tools to continue to produce world-leading science at the facility, and to try to amplify our resources through targeted collaborations. And so we've been able to really drill down into a number of tactical areas or functional areas that involve really everything in computing at the facility, from networking infrastructure to data management to software to how we can leverage AI and ML better. And so what I'll do is just talk through some of these vignettes in terms of some of the exciting developments that we've made at the facility. We have an entirely new network infrastructure that's been deployed in terms of the Beamline side, including all new network switches, a brand new fiber plant, new cabling to Beamlines, and even plans to increase the link between the APS and the on-site supercomputing center to a terabit per second link. A lot of this might sound kind of boring in a way in terms of networking cables and things, but it really provides the backbone for us to be able to handle and process all of the data that we collect at the facility. In terms of controls and data acquisition and detector integration, we're targeting advances in 3 areas: fast scanning and feedback, fast detector data handling, and modernizing our experiment control platform. So for fast scanning and feedback, many of our new scanning probe instruments really require this to be productive. And so we've developed software at the APS called SoftGlue Zinc, which sits on top of FPGA hardware and acts as an interface into EPICs for programmability in terms of FPGAs. For fast detector data handling, we have developed a streaming framework within EPICs called PVA-PY that relies on EPICs version 7 and integrates with Area Detector. And this allows us to be able to stream through the EPICs infrastructure high bandwidth data from detectors, but it also allows us to coordinate different data streams. So we can coordinate data from detectors, things like interferometry, other kinds of machine information such as energy, and that allows downstream applications to have all of the data they need to do real-time data processing without having to do their own data wrangling. And then finally, in experiment control, we're working towards adopting blue sky at more beamlines. And so you just heard a great talk by Eric on this, and then tomorrow you'll hear another talk by Fanny in more details about our strategy and the progress that we've made there. Data management is very important to us. The APS has a facility-wide software and hardware infrastructure for data management that we have creatively called the APS Data Management System. This is what manages transferring data from acquisition devices to computing infrastructure to storage. This is also what maintains access permissions for our users. And in the past few years, we've put a tremendous amount of effort into developing workflows that are integrated with the system based on the Globus Compute workflow infrastructure. And so you'll hear a lot more about this on Thursday. Ian Foster is giving an invited talk here about kind of the high-level perspectives on this. Hannah Paraga will go into much more detail about our data management system and work that's been done to develop workflows in that space. And then Justin Wozniak will talk about resiliency for workflows. We're taking a multi-tiered approach to computing hardware and infrastructure that we need to process data. We are trying to explore edge devices, what can be done in that space, especially with AI inference that we can run at the edge. Of course, Beamlines have lots of workstations for first-pass data processing, and we do maintain a modest-sized CPU cluster at the APS. But as data sizes increase, the data rates increase, a lot of our techniques need high-performance computing to be able to keep up with the data that we generate. And we're really lucky to have on our campus a supercomputing center called the Argonne Leadership Computing Facility. And they've recently deployed a supercomputer a few years ago called Polaris. It's a NVIDIA-based supercomputer, and it's about 44 petaflops in terms of peak performance. But the thing that's really interesting for us is that there's a carve-out on it right now of about 10% of the system that is meant for on-demand computing, real-time on-demand computing from facilities like the APS. And so we basically have priority. We can submit a job if something is running on that 10% of the system. Those things get killed, and then our jobs run. And so a lot of the workflows we've been developing are targeting this platform. The ALCF has recently just rolled out an exascale supercomputer called Aurora. And as that comes online, we're going to transition that 44 petaflops to be fully on demand for use by experimental and observational facilities. So that's really a great partnership that we've had between our facilities. We're also upgrading our data storage infrastructure from about 8 petabytes to a new 50 petabyte disk buffer so we can write data directly from detectors. And we've been taking advantage of the ALCF's tape storage library for long-term data retention. Or I should say longer-term data retention. But you'll hear more about that tomorrow. So data reduction and analysis software is very important, right? Because we need to get results out quickly. And so we've been focusing most of our efforts on the techniques that are going to be needed or will be employed by our feature beamlines to make sure that as those come online and are commissioned, the users at those beamlines will begin to get reduced or reconstructed results that they can then use to begin to interpret and do science with, right? So we've been putting a lot of effort into XPCS software, tychography software, Lowy depth reconstruction software for crystallographic orientations, multimodal diffraction and imaging data as well for grain structure and orientation. And you can see all of the beamlines listed that these will be used at. Fluorescence mapping software, tomography software, Bragg CDI software, reciprocal space mapping software. And so for all of these, we've taken the approach that, we've been writing these as parallel applications that run on CPUs or GPUs if they lend themselves to that. And then we've developed workflows for all of these that run on our supercomputing center. Let's see. So AI and ML is, I would always say it's an emerging space, but it has emerged already. And there's a lot of potential for our facilities to take advantage of this. And you've already heard some talks. But we're targeting kind of 3 main high-level areas for this to leverage AI, ML for data reduction. for experiment steering, and then for knowledge extraction. So in the data reduction space, we've had very good results training neural networks to perform data reduction faster than conventional approaches could, for all else being equal, the same amount of computing power that's available to them. So our colleagues have worked on TychoNN, which is a machine learning tychography reconstruction package that runs hundreds of times faster than conventional methods. BragNN, which does a really good job with peak finding and is high performance. Groups have been working on smart data acquisition. In this case, in the middle, you see the use of Google's tools for smart scanning to pick the next points. This allows us to get better coverage, and it reduces beam damage because we don't have to sample as much. And then we've even had groups working across the lab on things like generating interatomic potentials using machine learning for higher level science applications. So collaborations are very important to us. Over the years, the light sources in the US system have been working very closely together. We've been developing strategic plans in the area of computing, kind of coordinating work amongst ourselves. And very importantly, we've been developing a lot of reports and guidance back to our sponsor about what the challenge areas are here and what the value proposition is for addressing the space. We've developed a common data policy template. Most recently, we've more formally included the neutron sources in the US in this collaboration. So the spallation neutron source and the high flux isotope reactor as a neutron source from Oak Ridge. And we've been working together very recently, especially on coordinating proposals for funding calls. And we actually have developed, I think, a very comprehensive portfolio outside of our operations budget in terms of additional funding, especially looking at the AI/ML space. So these are all funded projects that are going on within the Department of Energy landscape. And most of these are collaborative. So many of our facilities work together on them to deliver the output. So this is my last slide. There are a number of other opportunities in this space, especially in the US landscape. And these are three of them that I kind of want to talk through right here. The first one is called the Integrated Research Infrastructure Program. So this is actually a funding program or a new funding program that our sponsor is launching right now. And the aim behind this is to provide infrastructure and tools that help large-scale research facilities integrate better with each other. So the actual I would say deliverables are still yet unclear because it's coming into formation, but these are things like funding workflow systems, building blocks that we can then use to put together so that our facilities can interoperate better. The second project is actually a new user facility that is being constructed called the High Performance Data Facility. And so this is going to be a new supercomputing facility in the United States that focuses instead of large-scale simulations on data-intensive science. So it's meant to be a facility for the kinds of things that are emerging in terms of what our facilities need for computing. And there's a lot of potential in this space for resilient computing resources and providing things for our user community post-experiment. And then finally, the Department of Energy is beginning to launch a large AI initiative called Frontier AI for Science, Security, and Technology, or FAST. And so this is going to be a department-wide initiative of funding resources to better explore the use of all of the data that we collect at our facilities and a variety of challenging science applications on top of it. So this is really exciting for our facilities to try to leverage the data that we have for something bigger than what you would get out of single experiment. So with that, I just want to acknowledge that this is certainly not all the effort of one person. Across the lab, there are well over 100 individuals that are working on APS applications and in this space, either employed by the APS or from our computing collaborators or science collaborators at the facility. So I'm really, really honored and lucky to be working with so many people that are interested in this space. All right, so thank you.
Wow, thank Thank you, Nicholas. I guess we have, again, time for one question, maybe.
Maybe one question. You said you have on-demand access to the Polaris cluster. What is the latency to get the data there and have, well, the scheduling plus, well, how long does it take when you start a scan on the Beamline to get some data appearing over there to start processing?
Yep. So the scheduling system, it's only a few seconds, 1 or 2 seconds latency for the scheduler to actually change over a job for us. And then the latency of moving the data is really dependent on the network infrastructure that we have. And so I think there'll be some of the talks on Thursday, we'll discuss a little bit more detail on that. But as I said, we're planning on upgrading our network link to 1.6 terabits per second between the two facilities, which should provide fairly decent bandwidth for us. Yeah. Okay, great. Well, thank you.
Well, let's thank Nicholas again, and we move on to CERN.